Hi, so I wanted to give an explanation of zipWith, which is a very handy function in Haskell, and just like go through some examples of using it and explain what it does. So yeah, let's get started. Let me just increase the font. Hope this is a bit readable. Okay, cool. Now let's see. Okay, so zipWith, what is it? Let's see the documentation here. So it generalizes zip. Zip usually gets two lists and just for each element applies a function to both elements of each list. So it takes the first element and the second element, and the first element of the first list and the first element of the second list, and applies a function to both of them. That's what zip does. Now zipWith is kind of generalization of it. So you give it a function and it zips with that function as given as the first argument instead of a top-line function. So for example, zipWith plus is applied to two sequences to take the sequence of the corresponding sums. There are other variations, like this one is in data sequence. There is one in byte string, but the most important one is the one in list. So it generalizes zip by just zipping with the function given as the first argument instead of a top-line function. So for example, zipWith produces the list of corresponding, zipWith plus produces the list of corresponding sums. So let's see the signature of zipWith. So it just gets given a function, which is the function that gets passed in the first element of the first list and then the first element of the second list, and it returns a value, that is calculated by that function, and it gets given we give it the first list and the second list, and we get the final list result. That's all. Now let's see some examples. Let's see the simplest one, which is zipWith plus. So if we do zipWith plus on, say, this list from 1 to 5, like say 1, 2, 3, and on another list which has like 4, 5, 6. So we can see it added 1 to 4, which gives us 5, and then 2 to 5, which gives us 7, and 3 to 6, which gives us 9. So it's pretty straightforward. Now let's see this example here that I have. So what it does, so just a description, it just given a function pairwise on each number of both lists, and zipWith that function in both lists. It just evaluates to f applying f and given both arguments a and x, then f given b and y, and then f given c and z. Here we get that final list. So if we apply it to this here, where we want to just to get a list of zipWith by multiplying these two lists, zipping by, which means multiplying each element of one with the other. Same thing with the second element and with the third element. So let's run this here. So if we run that by just running example 1, we can see we have 3, 4, 6, which is just 1 multiplied by 3, 2 multiplied by 2 here, and 3 multiplied by 2. And the second element, same thing. 3 multiplied by 3, which is 9, 5 multiplied by 4, which is 20, and 6 multiplied by 5, which is 30. So yeah, so that is a pretty straightforward usages or use cases of zipWith. Now let's take a look at another example. So let's say we want to write a function that takes two lists and tries to divide each element of a list A by the corresponding element of a list B. And if the element in list B is 0, the element we want to divide by, then because that would give us an exception, we want to just return nothing. And otherwise, if it's not 0, we want to return the real division value. And so the way we write that, this is just the type signature here. We want to return maybe, because if it's 0, we want to return nothing. And we do a zipWith where we get both values of each list, x and y, of x of list A and y of list B. and we check if the value of in list B, which is y, if it is different than 0, then we just return the division, which is what has been described here. Otherwise, we return nothing, because that means that the element was 0. Okay, and so we can just apply that to this list here with the 0 value here, which means that the second element should give us nothing as a result, and the other ones should be just division. So if I run this, yeah, we can see that here we get 1, we get nothing, and we get 2. So it's very handy for these, for example, kind of things. Another example that we can take a look at is Fibonacci. So Fibonacci is just the first, on 0 is 0, for 1 is 1, and for n, any value, it's the Fibonacci of n minus 1 plus Fibonacci of n minus 2. This is like the exact definition of Fibonacci. Now, if we want to write it in a better way, we can use zipWith. So what we are doing here is just, we know that for any value n, we want to, if we want to get its zip, we need to just get the zip of these values. We can just concatenate them. So if here, this fibs here gets you like the list of all Fibonacci numbers. And since it's lazy, we can just do take and get a number of Fibonacci numbers. And so we can use zipWith to have this function plus, and fib n minus 1 is just, we can just pass in the sequence fibs itself, and for the previous element, which is the previous element to n minus 1, is fib of n minus 2, we can just take the tail, because if you look at the documentation of tail, it returns it extracts the element after the head, so we'll just skip the head, which is the n minus, which is the n minus 1 element, which means that we will get the n minus 2 element. And that's basically all that we need to do. So if we use our fib here, so let's take the 10 first Fibonacci numbers. We can see we get 0, 1, which is the ones that we got here, and then we get fibs and tail of fibs. So if we have 0, 1 as our list, fibs is 0, 1, and the list is just 1. So plus, the first plus is 1, and then the second plus is 1 plus 1 is 2, and we'll keep recursing until we get to the final number that we want to take. Now let's take a look at this other example. So we can have palindrome. We can also like check if one string is a palindrome by using zipWith. So a palindrome is a string where its reverse is the same as the string itself. Let's take any palindrome string. So let's say palindrome string examples. Let's just take, ABBA. That's a palindrome there. So we can check here palindrome. So that returns us true. If we use so if we use if we add C and the B in the middle, it's still a palindrome because the reverse is still true. But if we add this, it becomes false. And so the check for a palindrome is just, if we have this ABBA, we need to just reverse it. And if the reverse is the same, then it's a palindrome. That's basically the definition. So the way we are calculating it here is just by checking. We reverse the string, and then we take the string itself, and then we zip by checking equality. So if each element of the string and its reverse, each element, which is each character of the string, is equal to the other one, then that means that both lists are equal, because a string is essentially just a list of characters. And so if each one of them, each character in the string and its reverse is equal, that means that the string and its reverse are equal. And so we just do AND here to make sure that, because zipWith, let's do it on this ABA. So let's say, let's go here, so what we are going to do here is let XS equal to this. And what we can do is just to zipWith equality on XS and its reverse XS. So we get true for each element because they are equal, and then we can just do AND to check that every one of them is true. So if all of them are true, then we get true, and that's what we want for palindrome. So if we apply AND to that list there, we get true. If we take x to be some value that isn't a palindrome, say this, then our zipWith will have false values, and if we use AND on that, we'll get false. And so yeah, that's a pretty good way of doing it. Another example that we can take a look at is Pascal triangles, and we can just see how we can use also zipWith to calculate those. So the Pascal triangle is, the definition of it is just having a root element 1, and every other element being the sum of the 1 or 2 elements above it. So this one here has just 1 above it, so we just put 1. For this 2, it has 1 and 1 above it, so the sum of these two is 2. For this 3, it's 2 plus 1, so that's 3. And the way we can solve this is very simple. In Haskell, we can just use induction, right? So the first row of the triangle here is just the list 1 that has one element 1, and each row after that can be computed from the previous row by adding the row, like the sum of both the 1 or 2 above it, and that means just the previous row by adding like the shifted left and the shifted right value, right? So for example, for 2 it would be this one and this one, and so we can like directly translate this in Haskell. So what we can do is, so we know that we just need to shift it, so where there is nothing, we can just consider it 0, because that's essentially what it is. When we add nothing, it's 0. So we can just, for the shift, the first element has 0 and 0 with the end of it here, and we can just consider it that because we zip by adding, we add the two elements, one shifted to the left and the other shifted to the right, and so we can just zip with 0 plus the list, and then xs plus 0 on the other side, and we can just add them and we get the result. And thanks to laziness, we can just keep iterating, and we can just take as much Pascal numbers as we want. If you take a look at iterate documentation, it's just returns an infinite list of repeated applications of f. So here it will keep applying next infinitely, and we can just take how much numbers we want, Pascal numbers like we want. So if we run this, if we run like say next on let's say just 1, we should get just the next row, right? So 1 1, we get the next row here. If we run it for the second row, we get the third row. If we run it for the third row, we get the row after that, and if we run it for the last one, we can get that last one. So, and it will keep iterating, giving us each element. And if we use Pascal that we have there, and let's say take 10 rows, so let's say we use the Pascal function that we defined and just take 10. So that gives us 10 rows of Pascal numbers. Now, another way to write the same function that we wrote here, it just, so we have the first, so for each row we have 1 and 1, and then we have the others, 1 and 1 on the boundaries of each diagonals of each one. Each row has diagonals that start with 1 and end with 1, and we can just add like the ones in the middle are just the one above them, each one plus the other, and so that just means we add xs and tail of xs, which means skipping the first element. This is similar to what we did here for Fibonacci. It's almost the exact same pattern. And yeah, that way also we can calculate Pascal triangles. Another example that we can take a look at that I have here is, this is an interesting problem, and it's quite nice, the solution that we end up with using Pascal triangles. So let's say we are given an array of numbers called nums, and we want to return an array of numbers products, so the products of these numbers, where for each product, or in our array products that we want to return, for each element in it, index, it is like the product of all numbers in the array that we have as input at index j, such that j is different than I. So we want to get basically the product of all numbers except the one at the index that we are in. So for example, say we have this input 1 2 3 4 5. The output we want is for this first index, which is 0. We want to get the multiplication of all of them except that index. So 2 multiplied by 3 multiplied by 4 multiplied by 5. For the next one, we want to, which is for this index, we want to get multiplication of all the other except this index. So 1 multiplied by 3 multiplied by 3 multiplied by 4 multiplied by 5. And the same thing for this one, all of them except the one at index 3. So that would mean 1 multiplied by 2 multiplied by 4 multiplied by 5. And you get the idea. This is what we want, and we want it in a way that is at least even, and like not just go through the list once. And so an interesting idea that we can use for that is we can just construct two arrays that kind of starts with 1. Each one, so the first one starts with 1, the second one starts with 1. 1 is just because in multiplication 1 doesn't have any effect. And then we start with index 0, so we get the array, the input array value at index 0, and then the other one we continue multiplying, and then we continue multiplying. And for the second row, we skip so you notice for the first row we added 1 here so that we can skip the last element in the multiplication. And here we start from like the end, where we put 1 at the end, and we start from the last one, multiply by the one after that, and multiply by the one after that, and skip. Our goal here is to skip the first index. And after that we can just multiply those two arrays. So the first one would be multiplying A1, A2, and A3, which will give us basically multiplying this, and this. Let's say just to make this match the same number of elements, let's say this one is just this. And so for this 2 3, so for example 1 here, we would have just this multiplication of the first element of the first array multiplied by the first element of the second array, or second list. So that would make this be 1 multiplied by A1, which is 2, multiplied by A2, which is 3, multiplied by A3, which is 4, and so that will give us, let me fix this here. So this multiplication of this and this will give us this value. Multiplication of this and this will give us 1 multiplied by 3 multiplied by 4, and the same thing for the rest. So you can notice here, for the first one we skip it A0, which is the index 0 that we are at here, and for the second one we skip it index 1, which is the index that we are in here. For this one we skip it index 2, which is the index that we are in here. Same thing here, we skip it index 3, which is the index that we are at here. So by constructing these two arrays in this clever way, we managed to skip the index in which we are at for the values in the top one and the second one, which is pretty clever. And so once we have this solution, we can just implement it with zipWith. And you can see zipWith is just the way we take the element from the first one and multiply it with the second one. element of the first one multiplied with the second one. And so our solution would be just a zipWith with multiplication operator, the above array, this one, multiplied by the below array. And that way we get the final output that we want. And the way we calculate the above array and the below arrays is just so the above array is just by adding 1 to the array except the last element, and to get, or the list except the last element, and that's exactly what init does. So if you look at the documentation of init, it just returns all elements of the list except the last one, which is exactly what we want here. So we get all elements except the last one, we add 1 to that one, and we just keep multiplying each one of them by the other one, and each time we get the result. So we multiply first just 1, and then we get the first element, and then we apply this scan left multiplication, so we get a0 multiplied by a1, and then same thing for that value. For the below array list, we do something similar also. So tell it would skip the first element, which is what we want, and then we need 1 here, this last one, and we apply scan right so that we can start from the right. And so yeah, so start from the right, we have 1, and we multiply by a3, which is the scan right for xs. So and then yeah, and we do the same thing, we multiply, and the same thing that we did here for scan, and yeah, that gives us the final result, and we have a nice usage here of zipWith. So it's very useful, and I noticed that I used it a lot in a lot of doing a lot of exercises. So yeah, play with it, and yeah, you'll find it very useful. Okay, that's all that I wanted to show. Thanks. Bye bye.